Welcome, ladies and gentlemen. We are going to start in a minute or so. We'll just let folks joining. There's still a bunch of folks joining, so we'll let them catch up with the rest of you. Hopefully, we'll be starting in about 1 minute. Welcome, ladies and gentlemen. My name is Brian Patterson. I'm the president of eMerge Alliance, but today I'm actually working and representing the folks who are conducting a national trade show and exposition and conference called North America Smart Energy Week, which is coming up in September at the Salt Lake Convention Center in Salt Lake City. But today we'd like to do two things. We'd like to give you a presentation on some of the material that's going to be presented at the show, in particular on the theme of the grid of grids. So I'll make that presentation in just a moment. And then we're going to give you a little bit of a pre-show sneak peek at some of the stuff that you'll see there from a couple of our primary partners in the effort to stand up a live microgrid and some other demonstration things at the show. So without further ado, I'm going to jump into the presentation. We will hear from those three sneak preview folks in just a few minutes after I make the main presentation. The real question about the grid of grids, or the grid today, is there an evolution going on in the grid, or is there a revolution? And depending upon your perspective, I suppose that you can take either side. But actually, in the beginning, the power grids, as they developed, they were somewhat contentious. In the early days, there were literally thousands of utilities competing on the same territory for power using customers. But also in the rural parts of at least the United States, there were already microgrids being developed as early as and deployed as early as 1917 in the form of these rural power plants that powered farms and rural homes that were far, far away from the cities and the availability of any sort of a power system or grid. But as time went on, the things kind of settled down, and with the passing of during the FDR administration, the Rural Electrification Act, the grid was extended from cities. The territories were defined, voltages set, and so on, so that things kind of settled down on the power front. And as you know, we ended up with this magnificent grid. So in many respects, we could say that pretty much from after World War II, that time period, about 1950 or so, we all kind of could go to sleep and leave the power business to the utilities and other folks who were commissioned to provide power, a dispatchable form of power at all 24/7, to our homes and places of business, etc. But in the meantime, and more recently, we've been seeing some issues creep into this wonderful world of the power grid and the delivery of electricity. There's been an increasing use of electricity, and despite the very vigorous efforts to economize and make things more efficient, there's just more use for electricity. And as some of you know, with electric vehicles coming on the scene, we're likely to see even double-digit growth in the amount of electricity that needs to be delivered and consumed. There's also the question of our dependency on fossil fuels and some of the environmental impacts of the use of fossil fuels, although there's been some really excellent work done in making the use of those fuels much less stressful to the environment and more economic. But it does, in many cases, have us extending an infrastructure that is already somewhat overtaxed into areas that previously haven't been well serviced and so on. And this has also put stress on the infrastructure itself, as well as dealing with the people who are impacted when infrastructure means that they will be inconvenienced in some way. And then last but not least is probably the issue of threats to the infrastructure, and they can be either man-made or what have you, or accidental or weather caused. So I think you could just kind of sum all of this up and say that, you know, we've been having some issues more and more with the power system that have been started to be addressed in many different fashions. But as a very wise person who is noted for his comments on solving problems and his ability to do so, really points out that it's hard to solve a new problem with the same thing that we used to, that may actually have created some of the problems in the way that we provided earlier solutions. But the real challenge then is, can we take these two old ideas, the idea of grids and dispatchable power on a power system that reaches to every building in every place in the country, and this older notion also of separate microgrids that, believe it or not, the ones back in the 20s and 30s had battery stack storage and droop controllers and automatic startup and so on and so forth, and provided actually in most cases DC power to farms and appliances in those rural homes at the time. But could we take these two old ideas and kind of bring them up to speed by adding some smarts, particularly on the grid side? Although some would argue that one of the greatest features about our grid is that it was relatively simple. Some would even say it was dumb, and that's why it worked so well. It didn't really have to deal with complexity and so on and so forth. But be that as it may, with the complexity being thrown at it, if we add some smarts to it and then add some new technology, particularly on the microgrid side, and connect the existing, I'll call it the old traditional grid, with the new notion of distributed energy production and storage and so on, could we end up with a more sustainable grid of grids, where these two very historic and traditional approaches can be combined into one to make it a better solution all around? Well, newsflash for some of you maybe, but not for others, is this so-called grid of grids, old and new. This evolution is well underway. And while that may surprise some, it doesn't others, particularly those who are seeing this transition in the making. We know that the grid is getting smarter every day. Smart meters, smart switches, and smart protection all throughout. So that's happening on the grid side. And at the same time, the notion of microgrids are evolving fairly rapidly with new forms of energy generation and storage at the ready that are causing this to happen. But let's, for a moment here, let's see how this is all coming together, because there are still some clashes of technology that have to take place and some resolution of how it all comes together. And the way I'd like to approach that is to discuss microgrids in a little more detail. And microgrids are comprised of 5 major functions. Those functions include local sources, energy storage, energy management, circuit utilization, and local loads. But before we go there, let's go back to the beginning of where the whole power system started. Because in the beginning, the utility grids were what we all considered the power system. And a utility simply supplied power to a user, typically through some sort of a load panel or what have you, load equipment, that then distributed out into a building or a premise or a property to service loads. And since the power was generated as AC, primarily for purposes of transmission efficiency, it could raise and lower voltages fairly easily with transformers, which made transmission relatively efficient and distribution as well. AC was the game that everybody used. Particularly also the devices at the time were mostly resistive loads and motors, so there was well suited for this type of power. The only problem is if the utility for any reason lost the power service capability, typically not at the generating site, but somewhere in between in transmission or distribution typically, the net result of that was that the users would lose power as well. That essentially, since it was dispatchable and not backed up in any way, you had an issue. Unfortunately, if some of the loads were critical, you really need to come up with a different solution to deal with those critical loads. Might be refrigeration or process technology or whatever that needed constant electricity. Many people would use an internal combustion engine generator as a result, either fueled by a fossil fuel of some sort, diesel, gasoline, what have you, and connect that into the system in a way that would allow you to service the critical loads, at least on a site, while the electric service from the utility was temporarily not available. Typically, that's the way things were done, but as we all know, it's still, there were and continue to be objections to even using some of this type of generation capability, although it's been vastly improved and is coming more and more back into the, I'll call it, portfolio of local sources that we might be able to deploy. In any case, if I go back to the original premise that the utility was the only game in town, so to speak, people had the notion that maybe PV or solar would be the solution to the problem, and by simply putting an inverter on the DC output of solar panels and arrays, we could connect and feed that power back in, particularly when the sun was out. It typically, however, was not used to directly feed the loads at a site because it had to be synchronized with the power that was coming from the utility, or you'd have to include a static switch or a complete switch over to the solar, which is too variable. So in any case, that's what a lot of people do, and you can do the same with wind. Again, a variable form of power in typically resolved out in the DC, since it's not a synchronized form initially. And again, the notion was to net meter this power back to the grid and at least solve the problem of power shortages and things like load shifting and time of day, and the perennial discussion about the duck curve that everybody I think knows is where most of the power consumption is during the day. So it solved some of the problems, but not all the problems. Because if you had the critical loads, they were still serviced by the same system, which meant that if the utility power was not available for some reason, either in distribution or at the source, that the resources at the local level were not available directly to the loads on the site. I think, unfortunately, some of you remember that this is exactly what happened when Hurricane Katrina kind of ravaged New Orleans, and despite the fact that there was significant alternate energy equipment installed there, none of it was able to be used because the utility power was lost, and therefore there was no synchronized source of transmission for it. So talk about a shock, and that's what people were in when they realized that even though they had these distributed resources, they weren't available during those times. So then came the first generation, pardon the pun, of islandable controllers, or smart inverters. And what this allowed to be done is you could feed loads directly, and technically you might call this the first technical type of microgrid that was available. That is, if you looked at the Department of Energy definition, where a microgrid is defined as a group of interconnected loads and distributed energy within a defined electrical boundary, where it acts as a single entity of control with respect to the grid, you technically have a microgrid here. And better yet, it can be disconnected or islanded from the utility grid when there's trouble on that side of the meter, and still support local loads. So that's what happens when you lose utility power. You still then can manage the power through this smart inverter type arrangement. And there you go. You know, and this is great. As long as the sun is shining or the wind is blowing, you have power for the local loads. The problem is that if the sun isn't shining or the wind isn't blowing, you're out of luck again. So it's not really a backup. It is an alternative, and it is technically a microgrid, but it is not really a dispatchable backup that would allow you to continue to operate under any condition. So microgrid or not, it's back to square one. No power for the local loads under these conditions. So what do? We got to add storage. We add initially practical storage for many people is battery, either traditional wet cell type batteries or newer sources like lithium ion and so on. They can become a backup source of DC power. And since you're already converting DC from the solar arrays and wind turbines and such, coupling in a battery is a fairly straightforward thing to do. So now again, you're back in business, at least temporarily, until the battery runs out. And if the battery runs out and you still don't have solar or wind, and the utility is not supplying power, you're out of luck again. So no sun, no batteries, no wind, no power. So you need to charge those batteries, right? A simple premise. Charging circuits do need to be added. That means that the conversion equipment here is not just a simple inverter, but it also then is a DC charge controller. And whether it comes from the utility or from the local power sources, this DC power output from the controller can be used to manage the battery and recharge it as appropriate so that it's available when all the other sources are down. So other storage equipment like flywheels or capacitor banks and all that can be similarly added as appropriate and matching the use case that you have for storage to manage and provide this backup task. So when the local sources or the utility aren't available with a charged battery capability, if you size the battery system properly, you can have your backup for critical loads. In this case, an inverter is used to provide AC power to those critical loads. So next would be to look at, since we have DC power available, what about having DC loads? One would argue that the coming of electric vehicle fast charging, which is a DC premised process, that having DC in the microgrid is a good thing and may in fact be the app that starts to kick the loads over to considering a direct use of the DC that's produced in the local microgrid. Following, of course, electric vehicle, we all know that a lot of the appliances that we buy today are essentially DC electronic appliances, and therefore simple conversion of the power supply that feeds them to allow DC input would give a capability of DC local controls. Either they be critical loads or convenience loads, and many of you know that most convenience loads, like TV screens and computers and things like that, and other entertainment systems are also DC, so they can be similarly coupled in. So in many cases, you'd have now a hybrid microgrid that could feed both AC loads and DC loads, depending upon how the loads are configured. Again, if power was disrupted, both locally and from the grid, you go back on reserve power and you might trim back down to critical loads. And it doesn't matter whether they would be AC loads or DC loads. So that's the premise going forward. Now, in some cases, though, the availability of solar, which takes up real estate and needs to be mounted in a particular way, and wind is not available for some sites, particularly when you get into some of the urban sites and other difficult sites that don't have the space or facility to house them. So what do you do then? Well, one of the coming up and coming technologies that you'll see, in fact, at North America Smart Energy Week is the fuel cell. In most cases, people will be talking about either a hydrogen fuel cell or some sort of hydrocarbon-based fuel that can, like methane or something, that can be converted in a fuel cell to DC power. Again, the controller is sitting there, able to take in the DC, just like it could take in the solar or the wind produced DC, and distribute it back out to the loads. The question of then resourcing the fuel for that fuel cell is one that it can either be a delivered supply, trucked or piped, or it could be regenerated literally on the site. So if you had other sources, or if you took power from the grid and you had a fairly efficient recovery cell called a PEM cell, you could generate hydrogen on site, which then could be converted back to electricity when necessary. So you might look at this as hydrogen as a storage system and not just a power generation capability. Going from there, other forms of local sources might be combined heat and power generators, many of which are very efficient in running on, some running on biofuels, where you can combine the production of heat and power together economically to provide, in many cases, this will be a rotating generator, so it might be able to produce either AC or DC. I'm showing it as an AC generator here, going into the controller. So now it's available to the microgrid as a resource. Or you might have geothermal, thermal electric capability, which again gets coupled in this case, a DC output from the thermal electric stage of the geothermal. The nice advantage of geothermal energy is that it's contained or stored in the earth, and it is a fairly clean and highly sustainable way of generating energy. I think the economics aren't quite all the way there in many applications yet, but it's coming fairly rapidly, so we're likely to see more and more use of geothermal thermal electric conversion. And you can go back to the traditional internal combustion engine generation using more of the modern fuels and carbon capture technologies at the local level, which allows even the traditional synchronous generator to come back into the picture. So you can see the local sources are starting to accumulate over here, and painting the picture completely, adding back in the solar PV, some portion, maybe not all of it, maybe not the whole load can be carried, but a portion of it, and wind. There are many installations now that are combining solar and wind because of their kind of opposite time frame production capability. Solar obviously being predominant during the daytime and wind being more likely at night. So that gives an awful lot of capability on the load side, but take a peek over on the, on the source side. Take a peek over on the load side here, and I've added something called digital DC. This is a new concept that has been introduced to the market by a couple of companies, and we're likely to see more and more capability where we have actually a kind of a hybrid in a sense between AC and DC, in the sense that it is not a continuous DC, but rather a pulse DC or an interrupted DC that has the equivalent of 0 crossings at some greater multiple than 60 crossings like you see in AC, rendering it relatively safe or very safe as compared to either potentially direct DC or AC alone. So we're likely to see on the load side a desire to look at different forms of electricity using power electronics such as digital DC. All of that then leads to sort of a evolution of microgrids. As microgrids become more economic and more feasible and capable, this little microgrid that I just explained with all this potential sits in a building stock that is very traditionally not equipped with microgrids. But over time, I think we're going to see microgrids evolve not only in new buildings, but also in renovation, deep renovations, and other building renovations. I know about 50% of the microgrids that I'm seeing going in right now are building renovations and grid segment renovations, and the other 50% are new. That's kind of anecdotal information there, but I'm sure there are probably more new ones than renovations. But be that as it may, the proliferation of microgrids is taking place at an increasing rate. So then what do? You got all these microgrids out there. How about linking them together? Just as we found out or are finding out that linking disparate sources together kind of favors a non-synchronous approach, or what people will call DC coupling, where you take the DC outputs, match voltages or control voltages, and not worry about synchronization and so on, and line balancing. It's easier to couple things in. So it's logical that in a neighborhood where these microgrids are close by each other, and the voltages are relatively low, meaning dispatchable at the distribution level voltages that we are used to, and some even lower than that, that we would have DC links. And remember that although many of us were kind of taught a shorthand that DC is not good for transmission over wire or in any distance, really was a shorthand for the fact that you couldn't change voltages with DC as easily as AC. Well, that handicap is gone now with power electronics. So actually being able to raise a voltage makes DC at least equivalent, in some cases better, than transmission with AC. So certainly neighborhood DC links between microgrids are probably the simplest thing to do. And then add some communication from all the devices, or at least the microgrids one to another. You find that you have sort of a grid of grids at the neighborhood level. I like to think of the neighborhood grids as a sort of tier 2, tier 1 being a building or a property or a premise or factory, warehouse, what have you. Tier 2 being nearby assets, neighborhood grids, if you will, neighborhood microgrids that get connected together, but don't necessarily coordinate with the macrogrid. They, in fact, would coordinate through one of the microgrids or through a separate node as a combined entity at that level. And then, of course, we go to linking all of that back to the macrogrid, and we have, in a synchronous fashion, we have less synchronization problems, a much more balanced and level load, because we've now smoothed and averaged the load from these lower level grid of grids, and we end up with the end result being the grid of grids. And that end result, there we go. That end result, we like to call the grid of grids, but in this simple version, it really has 3 layers. It has the local microgrids, which can be islanded and operate on their own, but they can be linked together. Typically are going to be non-synchronous DC links up to a second level or a second tier of microgrids, again, which can be islanded as neighborhood islands, if you want to call them that, or community islands of power capability, and then linking that up to the traditional macrogrid or the master grid, which then has the resources. It sort of becomes the cloud of power, as you might draw the simile to the internet and the cloud of information. So you have the capability throughout. The lower level tiers can service the upper level tiers, particularly do things in grid support, can minimize disruption and so on. And here's a kind of a list of what happens. We believe that in this scenario of the grid of grids, that most new power capacity that will be added to the power system, the overall grid, is going to be generated at the fringe. That less of it is going to be at centralized power stations, generation stations. Most new generation storage and loads are also natively DC or direct current, which means that you have a different capability at the fringe than you traditionally do at the core or at the larger power centralized power plants. This notion of DC coupling, therefore, can be accomplished and really minimize the impact of distributed resource integration. So rather than have individual resources that have to be synchronized to the grid, which, as many of you know, because of the lower frequency momentum, as people would call it at the fringe, have a fairly significant impact on the operation and the quality of power at the fringe. But by coupling them in a non-synchronous fashion and then presenting less variables to the synchronous grid, this disruption impact is far less and the integration is much easier. Also, this notion of having layers of microgrid in a mesh topology or a non-centralized topology means that sections of the entire power system can operate independently and, in fact, work around any problems in the overall grid of grids, and then self-heal or come back online and reconfigure as the failures in whatever level in the system are resolved. So this kind of will move us away from these linear dynamic failures that we see where cascading faults run through the system and roll up to rather large interruptions. The semi-autonomous distributed control in this kind of mesh topology, we believe, will be accomplished not by hierarchical control, but by transactional management within the mesh itself. And transactional management is a subject that we could probably talk about in a whole other webinar, but suffice it to say that it really negotiates power, supply and demand, and value at the lowest level in this tiered structure as possible. And by doing so, you manage power flows essentially through communication at that lowest level. As a result, also, and you can see the versatility of all the different types of sources that we had, and the fact that we have a non-synchronous core, which then leads itself and lends itself to better final quality output of power that's not impacted by other parts of the system. There's a higher capability of differentiating the power quality and other services, voltages and things as a service, as opposed to the kind of uniform commodity that it is today. So we think that the grid of grids, with all of its microgrid architecture and mesh architecture, is going to help lead to energy as a service and this differentiation, which then will make the energy business a far more sustainable, economically sustainable business for everybody. In any case, that's the presentation on the grid of grids, but I want to emphasize that if you want to see some of this literally demonstrated at live at the Smart Energy Week, that's going to be in September in Salt Lake. We'll have a standing microgrids, actually several microgrid controllers will be demonstrating. We'll have a functional demonstrator, a 3D demonstrator that sits next to the live microgrid that will be going through the various scenarios that can be handled in the grid of grids. We're also going to be issuing and letting people try and learn in a try and learn format something called a Micropedia, which is a walk-away electronic self-directed microgrid encyclopedia. So if you want to know all about microgrids, anatomy, technologies, applications, how they work, value propositions, business models, etc. All of that's going to be in this electronic Micropedia that you can try at the show and walk away with as an app on your phone or laptop. We will also be presenting the Department of Energy and SEPA's results from their plug-and-play DER challenge. There are 3 finalists, and they will be demonstrating the plug-and-play capability of DER monitoring and management. And we'll also be hosting the Department of Energy's award ceremony for their American Made Challenge Solar Prize Demo Day, where they'll be announcing the winners, the winning teams that will receive $500,000 grants and the $75,000 vouchers that go along with implementing some of this solar work. So in any case, that's what we'll be doing at the show. And now what I'd like to do is move on to our other guests today and show you some of the things that they will be talking about and demonstrating at the show. So first up, I'd like to introduce you to a company called CE+T Energy Solutions. They are providing energy solutions literally, as their logo says here, at the grid edge. And from CE+T, happy to say we have Mario Barbaresso, who is the president and CEO of the Energy Solutions Group, rather. Mario, are you there?
I am there, Brian.
Okay, great. Could you tell us just a little bit about your background and how you got into this area?
Yeah, 30 plus years in the industry, from backup power to the energy sector. So I've always been involved in watts and VARs and whatever it is.
Okay, and CE+T Energy Solutions, I think hopefully some of our guests will know about that, but what exactly does CE+T Energy Solutions do?
Well, we are experts in designing and manufacturing power conversion product.
Okay. Are you there, Mario?
Yeah, I'm still there.
Oh, okay, sorry. So, and you serve a lot of different markets. What are the markets emphasis that you have for your company?
We're really we are present in the telecom sector, the data center as well. Working a lot also with C&I customers for microgrids, energy storage. So everywhere, every time you were talking about some power conversion product, including a complete solution with batteries and EMS, this is where we are.
And I can't go without mentioning that you were the winner of the Google Challenge for the little box challenge.
Yes, thanks. This was actually us winning a very difficult challenge of integrating a 2 kilowatt inverter in a matchbox. So we were very proud of that success.
So what is the technology that CE+T brings to bear to do all this power conversion?
Well, one of the greatest patent we have, and it's getting very popular in the industry now, is a 3-port converter, which combines, actually it's a bidirectional 3-port converter, which could be seen as an energy mixer between AC and DC. So it combines inverter and battery charger as well. So it makes the microgrid very easy to design, basically. It's an integrated solution, as you could see by that drawing.
And this is, I mean, some people think of power electronics as relatively small, but at least the slide that you have here says you go up to the megawatt range.
Absolutely. I mean, what we do here is obviously by module. It's a modular solution, so we can add them up to 3 megawatts. And again, each module has bidirectional inverter and bidirectional DC charger at the same time.
Wow, that's pretty exciting. So exactly where have you deployed some of this?
Around the world, from 200 kilowatt to 5 megawatt projects for data centers, utilities, C&I customers. As you can see here, we have different fit, form, and function. It could be for peak shavings or load shiftings, energy storage. That's where those projects were.
Oh, that's fantastic. That gives you a pretty wide portfolio. So that means, and most of these are turnkey solutions, or how does that work?
That's correct. We also have the possibilities of doing installation, commissioning, site monitoring, maintenance, and so on. So we're trying to wrap up our solutions with the proper customer support, basically.
And what we're seeing is that microgrids can be relatively complex assemblies of all types of different equipments, both on the supply or storage or load side. So assumedly you have some partners you work with?
Yeah, as you could see here from that slide, what we'll be presenting at the SPI show will be what C+T is currently doing with some of our vendors, and you'll see solutions already installed in demand response, peak shaving, energy storage, and microgrid. So you'll see some pretty creative modular power systems with all of our partners involved either in data centers and the energy sector as well.
That's absolutely great. I really want to recommend to people who are listening today to come to the show and see, because I know we've only spent a few minutes talking about what you guys do, but it is a lot, and it goes in a lot of different directions. So I hope they come and talk to you and your team at the show and see the live demonstration. You guys have been really supportive and great partners to help SEPA and SIA and the rest of our organizations, eMerge, to put together this demonstration.
Thanks, Brian. Looking forward to it. Bye-bye.
Okay. Next, I have a representative from West.net, another company maybe you have heard about, depending upon if you've been in some of their market sector. But as the microgrid evolution/revolution takes place, West.net is finding itself in new and different places as well. And we have today Joe Magno, who's going to talk a little bit about West.net. But before you do, Joe, tell us a little bit about yourself.
Well, thanks, Brian. Thanks for the nice introduction. I've been working in IT most of the time. However, about 20 years ago, I got involved in manufacturing and also data center technology, and began to realize that energy was very critical to these, what we call mission critical operations. And that's what brought me to West a few years ago.
Great. Thanks, Joe. And West, I know it's an acronym, but really West does a lot of different things. Exactly what do those things include?
Sure. The company's over 40 years old. Over the 40 years, we've had about 5,000 or 6,000 engagements. And over time, we've basically been involved in asset utilization management tools for mission critical facilities. The circle that's on the slide is really the four things we do. We'll do critical facility assessments. We also work helping with pre-engineered facilities. We'll do a lot of work in energy intelligence and analytics and asset utilization. So most of our clients come to us because they're looking for more resilient solutions and more efficient solutions.
Great. And I know you have sort of a philosophy of how you operate, or what your goals are.
Well, thank you. Well, much of what we do involves partnerships, but we believe that when you're implementing a microgrid solution, or even in any mission critical facility, knowledge is true power. So over the past 20 or so years, in working with many systems, we have developed a number of what I'll call APIs that allow us to speak to many different types of equipment. In other words, we're the Switzerland. So we can utilize any piece of equipment, analyze it, and bring it into a database. So the bullets on the slide talk a little bit about what we can do. We avoid what we call cross-platform dissonance. In other words, some of these facilities will have different manufacturers scattered all over the facility. Each one of them speaks a little different language. What we've done over the past 10, 15 years is develop translators for all of those disparate systems that allow us to tie them together in a very sensible way. And what you can see on the left-hand side of the slide are some of the dashboards we'll create that integrate different types of equipment, from generators to storage to basic equipment on the factory floor.
It's interesting because this is one of the points that a lot of people make, is that the microgrid world is a relatively complex world in the sense that it tries to integrate things that were never integrated before, coupling information that's coming from loads and sources and storage and so on, as you call it, across the platform. So this ability to simplify and get a sort of a total picture of what's going on relative to electricity and energy in general in a facility, I guess, is pretty important to folks.
Well, it's been very helpful to us over the past year or two because we can connect these together.
But the buzzword these days, I guess, is resilience. So how do you play into that genre?
So if you want to develop a resilient and adaptive microgrid, you need to have knowledge, and you need to have a good command management system. So our translators and our basic knowledge of how these things work allow us to give people real-time situational awareness and develop resiliency. And we can protect those microgrids. So we can deploy geographically and operate independently. One of our clients has 1,200 data centers that we can take a single look at. And they can do alarming, et cetera, across those.
So what are people going to be able to see at the North America Smart Energy Week relative to you and your partners?
Well, as you might imagine, Brian, we have a number of partners, but two of the partners that we're bringing in is Eaton. We use Eaton's Forcia product. We're their largest reseller and integrator. And we'll also be showing a product set, which we call the Foresight Suite, which is really a partnership between us and a company called SAS that does analytics. So we're now integrating with Foresight predictive analytics so that we can look forward and predict anomalies and predict what I'll call maintenance problems before they show up, utilizing that high level of predictive analytics that SAS produces.
That's
Both
fantastic.
of those products will be there.
Fantastic, Joe. You know, there's so much more we could ask you, and you know, I'm sure you could tell us about what you guys are doing. But again,
come to the show.
Yeah, just remind people to come to the show. Exactly. They can see it live. Again, we've worked very hard for the last several years to have a live microgrid at these shows, because otherwise, you know, it's not real until you see it actually working and doing what people say it should do. So thank you very much, Joe, for giving us a sneak peek at what you're going to have at the show, and we'll see you in Salt Lake.
Thank you, Brian. Looking forward to it.
Okay. Next, I have the pleasure of introducing Paul Savage, who's the CEO of a company called Nextec Power Systems. And Paul, I'm going to ask you to say a few words about yourself and your company, but to just kind of frame it for people is that we've talked a lot about combining and converting power and the sources and storage and so on, and monitoring and so on. But you're focused a lot on the load side and what happens with the power coming out of a microgrid or as it goes into even sub-levels of microgrid. So can you tell us a little bit about yourself and about Nextec?
Sure, happy to. Thank you, Brian, and good afternoon, everyone. I came to Nextec through a 2-year stint with Caterpillar Inc. out in Hanoi, Vietnam, where I was surprised most of our business was in base load and emergency backup power systems. And so when I came back home to New York, I was very interested to meet the founders at Nextec, who had developed these ideas around DC microgrids back in the 90s at the Brookhaven National Labs. So there's been a lot of water under the bridge since then. If you take me to the next page, I'll point out one of our premier installations there, the American Geophysical Union in Washington, D.C. You can learn more about that at building.agu.org. And that is a DC bus architecture with solar added to it as direct current. And most of the building load is DC. As Brian mentioned, Nextec is focused on the load, believing that unlocking that last conversion most devices require is the key to extracting all of the benefit out of this architecture. So we now provide driverless fixtures with some of the largest and smallest LED manufacturers in the business. We probably have 15 manufacturers now making thousands of fixtures for our specification. And it's become highly economic for customers by taking the driver out of the fixture. Our power supply can drive 30 to 40 light fixtures without a driver. That means there's nothing to break in the light fixture itself, just the LED light engine and the bent metal And so we're providing a 10-year warranty on the fixture. Next slide.
And I know for years, so just before I change your slide here, I know for years people have talked about, you know, how long LEDs will last. What a lot of folks didn't tell you is that the drivers that you had to use to convert the AC to DC and regulate that into the LEDs was what was going to break on you. So like you said, the warranties aren't as good as you would expect them to be based on the pre-advertising of LEDs. But it sounds like you solved that problem. So what else? What else are you doing?
And you know, in a parallel comment, Brian, the whole idea of portable AC to DC converters is another area that we're focused on, as you'll see in a minute, and as we'll demonstrate at the show. We have DC power outlets that are a part of our DC power distribution system, and so unlike the outlets you may have seen at the airport with a USB-A connector, that is a local conversion of AC to DC, and we actually have no AC to DC conversion at the device. So this slide shows how we right-size the electrical infrastructure for a building. If you see that the biggest box there would represent a building with conventional AC loads and AC circuits. And we find that we can avoid the installation of about 25% of the circuits normally dedicated to lighting and controls by using current limited power supplies the way we do. And now we see a similar reduction in circuits, sometimes greater, for our DC outlets. On the next page, you'll see I've broken into your homes and taken a picture of the receptacle at your kitchen breakfast bar. This is a great example of how our increasingly efficient load has really made the power infrastructure that we use less and less usable. This is an example where I've got about 40 watts of load struggling to get into a 180 watt outlet, leaving that receptacle almost 80% underloaded versus its rated capacity. So we can solve that, and I'll show you on the next slide that receptacle on the right, not actual size. It's not to scale there. It's not a 3 foot tall outlet. I did that just for clarity. That's the outlet we bring the Class 2 power to, and that's available in a modular office system. A mock-up you see there on the left, which is exactly what the American Geophysical Union has done, is they've brought that DC receptacle to the desktop. And of course, the two examples of the lighting and control that we also power. And we'll be showing examples of different fixtures and DC outlets at the Smart Grid Microgrid.
So that, if I understand that receptacle, it looks like you have two kinds of USB in there, and you also have a barrel connector, which I know is on my computer. So that, is it really that kind of universal that you can just have multiple different forms of the power there?
Well, one of the most interesting things about the development of the last 10 feet of power distribution in the last 5 years has been the success of the USB connector. You're right. You can see the top connector there is a USB-C connector capable of delivering 90 watts, and then two USB-A connectors, which are the most common portable device charging interfaces. And then at the bottom, that 2.5 millimeter barrel connector is actually programmable. So we can handle, as you say, laptops that require it, or legacy loads like a monitor on the desktop.
That really takes a notion of having just a single fixed voltage, because it would seem that you have to have at least 2 or 3, maybe 4 different voltages that you can service there.
That's right. Well, you got 3 in the USB-C, a 4th in the USB-A, and a 5th in the barrel connector. So that is a lot of flexibility there at the receptacle. And so when you come to the booth at CPI in Utah, all you need is a cord. You can leave your power conversion device at home.
There you go. So rolling all that up together, give us the punchline.
Well, we're at a point now that we've been able to lower the cost of these systems below conventional AC and DC AC lighting and control systems, rather. They go in faster. That's part of the savings, up to 50% fewer hours, because the Class 2 system does not require conduit or junction boxes or switch legs. It really is highly streamlined. And of course, lower operating costs. It's been a feature of our systems for years that they are more efficient and more reliable. That allows us to provide a warranty of 10 years, which is industry leading. And it's really proven out by the fewer number of components that is apparent to anyone that reviews what we're doing. So I'm looking forward to walking people through both the lighting, the controls, and the outlets as possible elements of their future projects.
So I know on the side you told me that although it's a bit of a chicken and egg thing with DC and DC available loads and so on and so forth, you do have a bunch of happy customers who are heading down this path of DC microgrids in their buildings, huh?
It's true, and some of them are also moving towards DC as a standard in their facilities portfolio. You know, facilities managers are loath to have different kinds of systems in their buildings, and we've been really happy to find portfolio customers with lots of real estate are finding these DC systems to be the direction in which they want to move, large and small. And some are from the DC domain already, like the phone and cable companies, computer companies, but also manufacturers, U.S. government agencies. We see it as a really broad movement going forward.
Well, that's great. I don't know how many people have actually experienced this kind of thing yet, but like you said, there's a number of places that they can actually start seeing this type of equipment, the systems being employed. But for sure, they can come to North America Smart Energy Week and see it all there. So thank you very much, Paul, for this. I'm sure that there's going to be a lot of people who are going to be interested in exploring the load side of this whole equation with you and your team at the show. So with that,
we're looking forward to it.
Okay, with that, I don't know if we've had folks who have questions. My associate here is telling me we do have a few. Okay, so one of the questions is where or how do generators come into play in regards to microgrid integration? Do all microgrids utilize generators? I'm going to assume that generator is the broadest of terms, meaning that you know, it could be a rotating generator, more traditional maybe thought of a generator, or it could be something like a solar panel or a wind turbine or a fuel cell or whatever. And the answer is all of the above can come into play in the construct of a microgrid. Essentially, one of the beauties of a microgrid is that it is literally intended and architected to blend. I think Mauro used the term, you know, kind of mixing, or the mixing pot. It's to blend all these different relatively disparate sources, some AC, some DC, together and make them available both for storage purposes and for utilization, immediate utilization, or net metering for that matter. So as I said, is one of the virtues of the grid of grids is that most of this new generation equipment and capability is likely to occur at the fringe of the grid and not at the core or at the centralized power plant locations. But I hope that answers that question somewhat. The other question is, how are mini grids connected to each other? Well, of course, this is an area that's being piloted and explored right now in a number of different ways. But the notion is that it is from a power standpoint, it's still a hard connection. So these links as I described them, most likely to be DC links, probably at voltages ranging, from well, in a traditional U.S. Type environment, would probably range from the 380 volts that I think was mentioned, all the way up to about 1500 volts in the local links, in the home to home or building to building in a business park or what have you. So from a control or from a control and monitoring standpoint, the links can either be hard links through the internet using TCP/IP protocol of some sort, or they could be wireless. And I think there's efforts in both those areas. And part of the demonstration that you'll see at North America Smart Energy Week is a demonstration of at least 3 of those higher level energy systems interfaces that are intended to allow the both the parts of a microgrid or microgrid to microgrid communication to coordinate all these resources. If you do that on the basis of a transactional balance, or as people would call it, a supply and demand balance based on value transactions, it can be relatively simple. There are more elaborate proposals for how that's done. But I think that it will probably resolve itself to be as simple as possible, and based on our learning from the internet and the rolling out of the internet over the last couple of decades, cybersecurity will be high on the list of requirements for that communication. The nice thing is that it may well be over the hard connections. So there are alternatives of combined power and communication on the same connections, particularly if they're hard connections from building to building in a neighborhood, which largely can be underground, or it may be some combination of electrical transmission and copper or what have you, and signal transmission through fiber. So there's several different schemes out there that are being piloted. But I think at the rate of what I'm seeing, at least, or what we're seeing at eMERGE, this is happening very quickly, and there are both proprietary and open source solutions that are coming into the marketplace as we speak. So I hope that answers that question. And I see that we're just past the top of the hour. So if there are no other questions, or if you have questions, I invite you to send them into me. You'll find my credentials on the eMERGE website at emergealliance.org. And I'll be happy to either try to answer the question myself or direct it to the folks who can. So again, thank you very much. I hope to see you all at North America Smart Energy Week in Salt Lake. It's a beautiful city. I've been there as we kind of did site survey, because we will, as I said, stand up a live microgrid, which, by the way, we will do in a 2-day period. So from nothing to a microgrid that will be servicing, supplying power out to the exhibits at the convention center, and probably backfeeding some excess power to the convention center itself for general use. We'll do all of that in a 2-day period. So that's it for today. Thank you for joining us. And also, you might look into exploring the world of microgrids at any one of the regional events that are conducted and sponsored by SIA and SEPA that we help orchestrate throughout the year. So thank you very much, and have a great day.